Thank you for coming to my talk. This is a joint work with my advisor, Nishit Vishnoi. Nowadays, data sets become much larger, and it is expensive to store or share the whole data set. And also, analyzing optimization problems over such data sets may not be efficient. And Coreset is a tool to address all these problems. And roughly speaking, Coreset is a small summary of the full dataset, and it can be used to approximately compute the objective. And due to the small size, Coreset has many benefits, like it can use to save the storage space and the computation time. And we consider the case clustering problem over a given metric space of endpoints. The objective is to compute a subset of k-centers such that the sum of the jth power distances from each point to its nearest center is minimized. And here are some special cases. If j equal to 1, we call it k-median. If j equal to 2, we call it k-means. And if j equal to infinity, we call it k-center. And our goal is to construct coresets for the clustering problem. Here, a coreset is a weighted point set. And given any subset of k-centers C, the weighted cost over the coreset S is a 1 plus or minus epsilon approximation of the cost over the full dataset. And note that these weights are necessary for construction. And our goal is to construct a coreset of size independent of n. And coresets have been well studied in the literature. I only list some very recent work here. And in Euclidean space, Friedman and Lemberg give a coreset construction for the general KZ clustering problem. Note that the size depends on the dimension D. And for k-means, Braverman show how to remove this dependence. And Solar and Ujov show how to remove the dependence of D for general KZ clustering. There is some result for k-center as well. For general metrics, Friedman and Lemberg also provide an epsilon coreset, and note that the size includes a log n factor. In general metrics, we cannot get rid of this dimensionality log n. But specifically, in doubling metrics, the dimension dependence is the doubling dimension, and in graph metrics, the coreset size depends on the tree width of the graph. Next, we overview existing approaches in Euclidean space. A widely used approach is called importance sampling. And we define the sensitivity of a point to be the maximum ratio it contributes to the clustering objective with respect to all possible center sets. Roughly, this sensitivity measures the importance of each point. And we approximately compute sensitivities of all points and take samples from a distribution proportional to sensitivities. And note that the computation time is only O NDK. And as mentioned before, this importance sampling framework leads to a coreset of size O tilde dk over epsilon to the 2z. Since D can be large up to n, and so we want to remove the size dependence of D. The idea is dimension reduction. We take k-median as an example and let OPT represent the optimal k-median value. Let this gamma be a subspace in Rd, and pi x is defined to be the projection of x to this subspace gamma. And for an arbitrary center set C, we define pi cx to be the projection of x to the spanned subspace of gamma and C. And Solar and Udolf prove that if for all set C, the total differences between two projection distances dx pi x and dx pi cx is small, say at most like O epsilon square times OBT. Then for any K-center set C, we can approximately compute the clustering objective with only by the projected points pi x. And concretely, we construct a projection f gamma from x to Rd plus 1, and which projects x to pi x, and the projection distance dx pi x. And for each center C, we project it to C0. Then we can see that this term is exactly the clustering objective over f gamma x. And since each point pi x is in the subspace gamma, we know that the n-bit dimension of f gamma x is only the dimension of gamma plus 1. This is an important observation, and if the dimension of gamma is low, then we can apply importance sampling on projected points to construct a coset. Unfortunately, Solar and Udolf also prove the existence of a subspace gamma of dimension only polynomial of k over epsilon that satisfies the projection property. Consequently, there exists a concept of projected points of size polynomial of k over epsilon. And then this coset size is independent of D. And we can further apply terminal embedding to reduce the coset size. The idea is to further reduce the dimension to 2 over epsilon square. And hence, there exists a coset of size O tilde k over epsilon to the fourth. This dimension reduction approach can be easily extended to general KZ clustering. It seems that, okay, now we have achieved a desired coset size. What remains? In the Solar-Udolf framework, we need to construct a subspace gamma. And the construction process is actually expensive and contains an exponential term to k over epsilon. And recently, this term is removed. Also, note that the coset is a subset of projected points instead of a subset of the original dataset. This results in a different computation function to the clustering objective. And if we want to solve the KZ clustering problem on the coset, we may need to design new clustering algorithms. To address these issues caused by the construction of gamma, we naturally propose a problem. Can we only use importance sampling to construct cosets, which is easier for implementation? And of course, the size should be the same as the Solar and Udolf framework. And next, we will introduce our main results and approach. This is an informal statement of our theorem. We propose a two-stage importance sampling framework that can construct an epsilon coset of size O tilde k over epsilon to the 2z plus 2. And the running time is only O tilde ndk. And note that for k median z equal to 1, this size is exactly O tilde k over epsilon to the 4th, which matches the size of Solar and Wuzhov mentioned before. And we also provide a lower bound for the coset size, say 2 to the omega z times k. This indicates that we cannot get rid of the linear dependence of k and the exponential dependence of z. And our first stage of importance sampling is to construct a coset of size polynomial to the k over epsilon, the same to the Solar and Wuzhov framework. But our idea is we do not need to explicitly construct gamma. Actually, the existence of such gamma is already enough for our analysis. And the second stage is again to apply the terminal embedding, and which can reduce the coset size to the desired coset size. And recall that we define the projected point to be pi x, concatenating the projection distance dx pi x. An important observation is that the sensitivities of x and f gamma x are the same. Hence, doing importance sampling on x is equivalent to doing importance sampling on projected points. And since on the projected points, we can construct a coset D of size a polynomial to the k over epsilon by importance sampling. And a natural conjecture is whether the inverse set of D, say S, is already a coset. Here is a figure for this idea. Okay, so recall we have these known facts. The clustering cost between X and C is roughly the same as the clustering cost between projected points and C. This is because gamma satisfies the projection property for X. And we also have this clustering cost between F gamma X and C is approximately equal to the cost 1 dc. And this is by the definition of cosets. So hence, if we can prove cos 1 SC approximates that cost 1 dc, then we are done. Since combine all these phase, we have cos 1 SC approximates cos 1 XC, and which shows that S is a coset. By Solar and Wuzhov, it suffices to prove that the projection property also holds for S. Say the sum of the weighted projection differences within S should be always small with respect to all center set C. However, the construction of gamma depends on X. Thus, it is unknown whether the projection property actually holds for S. Our main technical lemma is to prove this projection property, and here is a proof sketch. The first inequality is due to this mean operator, and the second inequality in fact connects the weighted subset S and the whole data set X, and showing that the total projection differences between S and X differ by at most O epsilon square times OPT. And the third inequality is due to the projection property for X. So this part is very small, only O epsilon square times OPT. And the main difficulty is to prove this second inequality. And the proof consists of two parts. The first part is to show the total projection distances to gamma between F and X is roughly the same. This is easy to verify since gamma is a fixed subspace, and we can use some like Hofstadter inequality to prove it. And the other one is to show the minimum projection distances from X to the span subspace of gamma and some center set C are roughly the same for the subset C and the whole data set X. And since the minimum set C is unknown for both weighted subset S and the whole data set X, the proof will be more technical. So our idea is to regard X as a point set in the orthogonal complement of gamma. And by this view, now pi Cx can translate to be the projection of X to the span subspace of C. Know that there are at most k points in center set C, so this dimension is at most k. Then dx pi Cx can be regarded as the projection distance from X to this subspace spanned by C. And this summation X in big X, this projection distance is exactly the subspace approximation value with respect to the subspace spanned by C. And by this observation, it suffices to prove F is a weak coset of X for subspace approximation. Unfortunately, this can be proved, and the size of F only requires to be polynomial to the k over epsilon as desired. And up to here, we complete the proof of the projection property for F. And it implies that F is a coset of X for clustering, and we can use importance sampling to construct the coset. Conclusion remarks. And our paper reveals a relation between two well-known shape-fitting problems, clustering and subspace approximation. We show that weak coset for subspace approximation and plus importance sampling leads to a coset for clustering. This relation may have independent interest. And our results indicate that importance sampling is already very powerful and can achieve nearly optimal cosets. Our work also leaves several open problems, and currently we still need 2 stages of importance sampling. Could we reduce it to 1 stage? And also, it is interesting to tighten the coset size, especially on the dependence of epsilon. Thank you.